Hello Chem 1, today we are going to use some of our prior knowledge about electron configurations, about the positive charge in the nucleus, to understand some of the periodic trends on the periodic table. Let's get started. So before we get started talking about trends, we really need to talk about why those trends occur. One thing you should already understand is that within a column on a periodic table, they have the same number of valence electrons. So for instance, the first column on the periodic table, they all end in sublevel S with one valence electron in that orbital in the S sublevel, and therefore they all end S1. The second column all ends S2. The 13th group or 13th column, the boron family, ends in S2P1, depending on which row you're in. The only exception here is helium, which ends with 2 valence electrons, even though it's in the 8th column. The same number of valence electrons is what gives these elements in a column the similar properties chemically and physically. That's important to remember when we're talking about these trends. Here's just a representation and showing you some dot diagrams. These aren't the dot diagrams how we do them, but you can still see that everything in the first column has 1 valence electron, everything in the 5th column has 5 valence electrons, and so on. We have also already talked extensively about the S block, P block, D block, and F block. I am not going to review that again here. You can see the picture on the screen. I'm sure you got this down by this point. All right, so based on that, let's start talking about some trends. Here are some of the trends we're going to talk about. You can see there's kind of a lot, and there's all these arrows pointing in different directions. Let's start off with the first trend, which controls all other trends. The first trend is called effective nuclear charge. If you think about the atom generally, we have a positive nucleus in the center, and then we have negative electrons. Well, opposites attract electrically. That means those negative electrons are going to be pulled toward the nucleus because of the positive charge and the negative charge. But there's another force happening here. It's called shielding. Shielding is the idea that we have inner electrons that are repelling the outer electrons. So if we look at this diagram, we have the nucleus, which is positive, and it is pulling these negative electrons inward through attraction. But if you have an element that has more than one energy level, that means these inner negative electrons are going to repel and push away the outer electrons. This is what we call shielding. So at any given moment, you have electrons being pulled inward, but also being repelled by inner electrons outward. So it's kind of this balance of this force, and effective nuclear charge, or ZEF, takes into account both of these things. So how do we calculate that? We take the nuclear charge, which is the atomic number Z, and we subtract the shielding effect, or the push outward, which is the number of electrons in inner shells. This would be every electron except for a valence electron. One way to think of ZEF is as the relative strength of each atom. In other words, how much strength is that atom, that nucleus, pulling inward toward itself? This is going to affect all kinds of trends across the periodic table. The nice thing about ZEF is it's similar within a family. So let's look at lithium and cesium. Lithium has 3 positive protons. It also looks like this in terms of electron configuration, and you can see that it has 2 inner electrons and 1 valence electron. So this would be 3 minus 2 to calculate it as a ZEF of 1. Cesium has 1 valence electron, and it has an atomic number of 55. So what this means is that we would subtract 54 inner electrons, because it only has 1 valence, and it would also have a ZEF of 1. This trend will continue across the periodic table. You'll notice that however many valence electrons an atom has, that's the ZEF, or the effective nuclear charge of that atom. So if the effective nuclear charge is the strength or the inward pull of the nucleus, and everything in the first column has a ZEF of 1, and everything in the 18th column has a ZEF of 8, then you should be able to figure out that the strongest atoms with the greatest pull inward are toward the right of the periodic table. Let's talk more about the alkali metals. Even though lithium and cesium have the same ZEF number, there is an incremental difference between their effective nuclear charge, or ZEF. Attraction still slightly decreases as you go down the periodic table because of increased shielding, meaning that since cesium has more inner electrons, it's going to push electrons away with a little greater strength. So yes, they're both calculated to be 1, but lithium would still be the stronger atom. It's going to pull with a little more strength inward. As I've kind of already said, as we move to the right on the periodic table, Zeph is going to increase, strength is going to increase. So look, fluorine is 1s2, 2s2, 2p5. So 2, these would be the valence electrons, 7, and the inner electrons would be 2. The atomic number for fluorine is 9, the inner electrons are 2, so the Zeph of fluorine is 7. So it's in the 7th column and has an effective nuclear charge of 7. Because of this, fluorine is going to pull inward with great strength. Fluorine only has 2 energy levels, but it has a large nucleus for those 2 energy levels with 9 positive protons. Those 9 positive protons are going to pull inward and make fluorine very strong and very reactive. This right here is very important. All other trends are based on Zeph. All other trends are based on effective nuclear charge and how much strength nuclei are pulling inward on their exterior electrons. It's important to know how to calculate Zeph, but the easiest way is just to identify it based on the column number. So for instance, calcium's in the 2nd column, so its Zeph is 2. Boron has 3 valence electrons, so it has a Zeph of 3. Sulfur has 6 valence electrons, so its Zeph is 6. Argon is a noble gas, its Zeph is 8. Potassium would be 1, carbon would be 4. Helium's Zeph would actually be 2, because helium doesn't have any inner electrons. But this would also mean that there's no shielding, and it's what makes helium a very strong atom. Now that we understand Zeph, we can start talking about some of the trends that are affected by Zeph. The first trend we're going to talk about is atomic radius. Atomic radius is exactly what it sounds like. It's really just the size of the atom. From the center of the atom, the nucleus, to the outermost electrons, what is that distance? And initially, it might just seem like the bigger the nucleus, the bigger the atom. But that's not how it works because of this inward pull. So as we look at atomic radius, let's first think within a family, and then we'll think across the periodic table. If we first look at the family, as we go down a family, shielding is going to increase, which means the smallest atoms within a family are going to be toward the top because there's less shielding. They're all going to have the same Zeph, but the atoms at the bottom are going to be a little larger because of that shielding. So if we look here at these examples, gallium is going to be larger than boron because it's closer toward the bottom. Iodine is going to be larger than chlorine because it's closer to the bottom. Krypton is going to be larger than argon because it's closer toward the bottom. And once again, barium and rubidium are going to be larger because they're closer toward the bottom and they have a greater shielding effect, which means they're not as strong. As we go across a period, Zeph is increasing, strength is increasing, but shielding is not. And therefore, as we move from left to right on the periodic table, atoms are getting stronger, and therefore atoms are getting tighter together and smaller. If we're choosing the smaller atom, the farther right atom will be smaller. Chlorine will be smaller than magnesium, neon will be smaller than carbon, xenon will be smaller than strontium, sulfur is smaller than aluminum, and tellurium will be smaller than rubidium. I'm choosing the element that is closer to the right because the Zeph is higher and therefore stronger and pulls in with greater strength, making the radius smaller. So if we looked at like a map of the atomic radii of the different elements of the periodic table, you can see that top right are small because greatest strength and not a lot of shielding, and bottom left have low Zeph and lots of shielding. You're going to see this over and over again as we go through these trends. Top right are going to be strong, and bottom left are going to be weak. That is how the periodic table is organized because of effective nuclear charge. So based on that, francium is the largest atom and helium is the smallest. Here's another representation. You will notice that the trend is not always followed. Remember, hydrogen's kind of an oddball up here in the top left. It doesn't really follow the trend. You're not going to have to remember the exceptions to the trend. Just know the trend generally and you'll be fine. The last trend we want to cover today is ionic radius. Ionic radius is the radius of the ion that an atom produces. The most important thing here is we got to remember the octet rule. All atoms are trying to get to a stable octet. When atoms have the same number of protons and electrons, it's neutral. But some atoms that are weak want to lose electrons. And other atoms, nonmetals that are strong, want to gain electrons. And that changes their ionic radius. Typically, weak atoms with low Zeph on the left side, metals, are going to lose electrons, and we call those cations. When they lose negative electrons, they're going to have a positive charge. So if they lose 1 electron, it's a +1 charge. If they lose 2 electrons, it's a +2 charge. Because they're losing electrons, because they're weak, it's going to be a smaller ion. The ions of metals are smaller than their atom counterpart. Nonmetals are the opposite. Nonmetals are very strong, and they typically have 6, 7 valence electrons. And because that, they're looking to gain electrons to get to a stable octet. When they gain electrons, they have negative charges. If they gain 1 electron, -1 charge. If they gain 2 electrons, -2 charge. Because they are gaining electrons, when they gain those electrons, their ions become bigger. Nonmetal ions, the ions are bigger than their atom counterparts. But metallic ions, their ions are smaller than their atom counterparts. This is a graphic that shows the atomic radius in gray. The color radius would be the ion radius. You'll notice that groups 1, 2, and 3, which are metals, they all want to lose electrons, and when they do, their ions are much smaller than their atoms. But nonmetals are looking to gain because they're strong. They have a high Zeph, and when they do gain, their ions are larger than their gray atom counterparts. So because of this, it says choose the smaller particle. With metals, the ion is going to be smaller because they're losing electrons to get to that ion. Same thing over here with cesium and cesium +1. But with nonmetals, the smaller particle is going to be the atom because their ions gain electrons to create the ion. Ionic radius is a little trickier because the trend is not the same across the entire periodic table. Metals do one thing and nonmetals do something different. And it really helps to understand Zeph, effective nuclear charge, and who's strong and who's weak to help you kind of solidify this information. Good job today. Make sure you spend some time with the activity. It takes a little while to digest this information and really figure out what's going on. And remember, it always goes back to effective nuclear charge, Zeph. Good job. We'll see you soon.